we are going to start the lecture on nanotechnology in chemical engineering. So today we will discuss about chemical method, that is the various methods we have discussed. So out of that, today we will discuss chemical method of synthesis of the nanomaterials or nanoparticles. So how that can be synthesis. So already these are the things we have already discussed. So today basically we will discuss Langmuir-blodgett methods for the nanomaterial synthesis and also microemulsion method, so that also can be used to synthesis nanomaterials. So here initially we will discuss about this method details, what are the materials are used for this particular method of synthesis, and then one or two examples that we will discuss, like cadmium sulfide, zinc sulfides. These are the in the form of nanoparticles, how that can be synthesized by Langmuir-blodgett methods, and also tungsten oxides, the nanoparticles can be synthesized. So these are the two examples also method of synthesis we will discuss. Okay, so let's start the Langmuir-blodgett methods. That methods actually has been proposed nearly 70 years back. So that was developed by Langmuir and Catherine Blodgett. So it was actually allows to thin organic films that can be formed by using this method, by using any type molecules or some long chains hydrocarbons having polar non-polar groups that can be forms a particular films. So that can be used for the synthesis of nanomaterials. Okay, so or nanostructure materials, or we can control the nanoparticle size shapes by considering different type of film formations with these methods. Okay, so in this particular type of methods, usually I said amphiphilic type of molecules that are used, different type of amphiphilic molecules are available, so per literature. So these molecules actually consist of one hydrophilic heads and another one is hydrophobic tails. So these molecules may consist of acidic or long chains methyls or methylene type of groups, so that present so in a single compound. So here you can see, for example, so we can see aracidic acid, so that is here this N equals to more than 14. So that carbons present long chains molecule, this is polar groups and this is non-polar groups, so present in a same molecule. So when that molecules is put in water, so water is a polar compounds or polar molecules, so then this is polar heads and this is non-polar tails of these molecules. So that polar groups will interact with the waters and then this type of shapes will forms, means polars interact heads that will interact with the water molecules, and then this type of means non-polar parts that would remain in the ears, and this type of means configuration of structures that may forms. Okay, so this type of amphiphilic molecules, considering the property of these molecules, so we can make a particular films, and also the inorganic materials may be any metal precursors, that is our interest to make a particular nanofilms or nanoparticles in nano range. So using this particular Langmuir-blodgett films, so we can use to synthesis nanomaterials. So here a few others amphiphilic molecules that is showing here. So here's this is one type of molecules and this is another one. So these are the long tails and polar head groups are present. So depending upon the applications or use or property are available, so that materials we can use any ones of these. These are modified, actually modified tail is modified with fluorides. Usually it is hydrogens, or it may be used with fluorines or others way also it can be changed. Okay, so whatever, so that amphiphilic molecules can be used to form the films. Okay, so in the step by steps I will discuss so how that film formations is there. So number one, so the step one is the monolayer amphiphilic molecules, that molecules will take in a particular solvents, so that would be distributed in that solvents and a monolayer formations would be there. And then second step is substrate that would be dipped into that liquid, so where that amphiphilic monolayer formations is there or molecules is there. Once that substrate that was dipped into that solutions, that would be pulled out. Okay, so once it is pulled out, so then substrate will be that amphiphilic molecules that would be attached with that substrate surface. Okay, so then Again also means if we one times dipped into that substrate dipped into that solutions, then one particular film formation should be there, LB films. And see if multiple times if you dip over that, so then one layer formations, monolayer formations is there, over that another layer formation should be there, like that multiple layer formations may be there. It means multiple times of depositions over the amphiphilic molecules at the same time, so that starting materials, if we use any metal ions, that would be also distributed that way, layer formations. Okay. So that way we can deposit that amphiphilic molecules at the same time, so that starting materials we have a interest to develop that film formations. Okay. So by repeating of this procedure means step 1 to step 5, if we do the repeats, so then multiple layers or many layers that can be transferred from solution to that particular substrate. Okay. So here step by step I am showing, so it would be much more clear. So how that amphiphilic molecules, this is dissolves in a solutions, and then this type of layer formations is there over the surface of the liquids. And then if we, this is a substrate, so if that is dipped into that solutions, so then that would be interact with that that amphiphilic molecules interact with the substrate, and then this type of formations would be theirs. Okay. So once it is take out that substrate, and again if we dip that one after one layer formations, another, this is tail groups, this is tail groups, that would be interact, and then it would forms another layers with that initial layer. So like that multiple layers we can forms over that surface of that substrate, and by that way we can synthesis the particular layers or films. Okay. So that can be used, this technique can be used to for the formations of nanofilms or nanomaterials or thin films we can produce. So here's the amphiphilic molecules that we have taken. So here's this amphiphilic molecules interact with each others by formations this type of layers. So it means arrangements of these layers, that may be three different types it has been observed, that X types, that is head tails arrangements, or head to head arrangements, or tail to tail arrangements, or tail head type of arrangement. Three different type of arrangements of these amphiphilic molecules when substrate was dipped into that particular solutions to take out that layers of amphiphilic molecules. So this is XX types, this is head, this is tails, this is head, this is tails, like that way these depositions might be theirs. Or Y types, that is head to head and tail to tails. So that way the arrangements, that is very common over the substrate, that would be when it is dipped into that particular solutions. And third one, the Z types, that is tail head, like that way also it may form. So when depositions only during removal of the substrate, this type of film formations is there. Okay. So now the key features of this particular LB type of films means, or Langmuir-blodgett type of films formation. So here's the deep order molecular order molecular arrangements. In this particular way we can orderly arrange that molecules that we want to form that layers. So here you can see that molecules, one molecules, another amphiphilic molecules interacted, and that type of films orderly arranged. So that basically due to the weak Van der Waals force of attractions that play for this type of layer formations, and in this type of layers usually it maintain 2D type of layers, that is the in this particular forms, and also the thickness that films that would forms during this LB method. So that is 2 to 5 nanometers. So if film thickness is 2 to 5 nanometer, very small thickness, so then that particular film we can use for preparation of very small nanostructure materials. Okay. So now we'll give some examples. So how these particular films can be used, or this technique can be used to preparation of nanomaterials of CDS or zinc sulfide by using this LB depositions. So here initially we said that our product is this or this. So then we have to consider initially cadmium precursor or zinc precursor, that may be any metal chlorides or nitrates, whatever, so that we have to take that we have to dissolve in water. Once that metal chloride dissolves in water form a solutions, and then we can add that surfactants or the amphiphilic molecules, so that would be make a particular way of arrangements, and then we can pass H2S gas, that would be converted metal chloride into metal sulfides nanoparticles. So this type of arrangements you can see that may forms with the surface of the films, with that would be attached, and by this way actually the nanoparticle that would be forms, it may be uniform size, monodisperse and well controlled in structures due to the surfactant stabilization. So in this case these amphiphilic molecules or surfactants that we have taken, so that orderly arranged in a particular manners, and thickness is very small, 2 to 5 nanometers. So therefore well controlled structures due to the surfactant stabilizations, and without, if we do not use any surfactant or amphiphilic molecules, normal way, conventional way also we can prepare, but in that case aggregations would be there and irregulars at different size of particles formations is there. However, by using a particular amphiphilic molecule or surfactants, so we can get well controlled structures when that particle formations is there. So next example is formation of tungsten oxide, so that nanoparticles that we can synthesize by using LB films depositions method. So in this case also, so we have to take a precursor means tungsten precursors that we have to dissolve, and then we have to use some amphiphilic molecules, that is surfactants, so that ODA, that is octadodecyl amines, so that is amine groups, and this is tails, long tails, that compounds that we can use, that would be dissolved in chloroforms, and then sodium tungstate solutions, that is precursor for tungsten, so that will form a Langmuir-blodgett type of film form would be theirs, and then we have to means solvents, whatever the solvents we have taken, so that we have to evaporate out in the second steps for 10 minutes. Then ODA means whatever the surfactant or amphiphilic molecules we have taken, with that precursor form a complex structure will forms, and then we can form a monolayers by dipping a Teflon's barriers or substrate we can use, and then we can form also multi layers, means initially monolayers we can forms, and then multiple layers also we can forms, 200 layers ODA tungsten LB films we can forms by multiple times dipping of that substrates into that solutions. That way we can make that multiple layers, and that can be transferred to any other substrates. So and then by heating or thermal treatments we can remove that surfactants or ODA that was taken, so amphiphilic molecules. If we heat it up or annals at 400 degrees centigrade for 5 hours, so then that would be decomposed, and then that films that would be forms or remains over that surface, that is nanocrystalline tungsten oxide, so that may forms over the surface, and that we can use for a particular process. So here schematic diagram is shown, so how the tungsten at oxide, the nanoparticles that can be formed by the LB film depositions method. So here's solutions, I said here chloroforms was taken, so ODA was dipped here, this is precursor of tungsten that was dipped into here and in the solutions, and then ODA was put in that solutions, and then it would be distributed, and then substrates that was dipped into that to make a particular films or LB type of films, and then we can multiple times also multiple layer formations is there, and then we can annealing or we can decompose or we can calcine that to remove that particular organics or others contaminations present in that particular film. So once that would be removed, then that materials or metal oxide left in the form of nanoparticles that we can collect and we can use for specific applications. Okay. So in these methods, I said the benefits is precise thickness controls, uniform molecular orderings, and ideal for nanostructures films, these LB methods. Okay. So next we will discuss about microemulsion methods. So in this case also we can two different solvents, one is oils, another in waters, usually they don't mix each others, but when in presence of surfactants we can also make them solutions, they can form a emulsion. So what is emulsions, that we will discuss, and then in this particular microemulsions methods we can synthesize nanomaterials also. So that we will discuss. So what is emulsion? So when two immiscible liquids are mechanically agitated, means in a beakers or any containers we can take two different solvents or solution liquids that may be immiscible liquids, and then if we start together they forms an emulsions. So that emulsions types also, that depends the quantity of each component or liquid that was taken. See if oil more, water less, or water more, oil less. So depending upon that different type of emulsions may formations is theirs. Okay. So the liquids which is small quantity, either oil or waters, that would forms droplets, or coagulates that droplets to forms a bigger particles. So usually the droplet that it forms in this microemulsions methods, that 1 to 100 nanometers within that range, the droplet formations are through microemulsions way. So that would be within that range, and that means microemulsions, that is oils and water combinations, that is smaller micellar type of things would form, so that we can use for the synthesis of nanomaterials. Okay. So here I am showing, so here's oil that was put in waters. So this is waters and this is yellow color, so that is basically oil. So oil quantity was very small quantity, drop 3-4 drops that was put in waters, and with that some surfactants. So surfactants is this blue heads and red tails, so that was taken. Then that water oil molecules in waters that may forms, so emulsion types of that they will organize like this way. So means surfactants will organized, means tail molecules that is interacted with the oils, and heads that is polar groups that remain outside. So that type of films or microemulsion formations is there. So when water is dipped or put into the oils, so there also this type of microemulsion formations is there. Also this type of micro bicontinuous microemulsion formations is there. So in initials of this case, so mycelial formations is there when water was excess and what oil was less quantity that was taken, and when water is very small quantity and oil was taken excess quantity, then inverse type of mycelial formations is there in presence of surfactants. Okay. So here's also another main things that will show the amphibial molecules when that was taken. This is aqueous solution, so water was taken and there's these surfactants we have put, and then surfactants will be distributed waters and airs. So within that, so this way, so the tail molecules remain airs and head molecules that remains dipped into the water, and this is when amphibiolic molecules that was spread over a aqueous solutions, then this type of arrangements would be theirs, and when means the tails distributed in airs and head distributed in water. So this type of means arrangements would be theirs, and when some hydrocarbons is molecules that are solution that was put in this aqueous solution, then hydrocarbon solutions separated itself from the aqueous solutions, since this is hydrocarbon solutions and this is water solution, both will be separated out. And so once both layer formations is there, then if you use or add some surfactants, then surfactants molecules that would be distributed amongst these two different solvents, and also they try to form some mycelia, means inverse mycelia or mycelia formations possibilities there. Okay. So what is mycelia and what is inverse mycelia, that already have discussed. So when water was excess and oil was a very small quantity, and when then mycelia formations is there, and when water was taken very small quantity and oil was excess, so then inverse mycelia formations is there, possibility is there. Okay. So now role of surfactants, means why we should use the surfactants, means without surfactants also can make that particles or nanomaterials we can synthesis, but surfactants that actually stabilize the emulsions, whatever the emulsions means oil and waters, when we stirrings and mixings them smalls, micelle formation is there. So what are the emulsions, microemulsions formation is there. So if you use surfactants, that surfactant stabilized these emulsions. So whatever that formations is there, small droplets or globules formations is there, so that would be stabilized with the help of surfactants. That is the role of surfactants. So now what are the different type of surfactants available, that we will discuss: cationic type, anionic type, non-ionic type or amphoteric type of surfactants. Many types of new surfactants also available. So most commonly used CTAPs, that is, or these compounds. So these usually used as a cationic surfactants. Also some anionic surfactants is also there, so that is sulfonated compounds, or non-ionics, that is fluoronic P123, like that of means alcoholic compounds. So non-ionic surfactants, amphoteric compounds also, that also non-ionic natures, that also used for the preparations of microemulsion. So I said the quantity of oils, water and surfactants, that depending upon oil water quantity, the micelle or inverse micelle formation should be there, or if we control or change the percentage of quantity of individuals liquids, water or oils, so then a different type of phase formation should be there. So depending upon that, different type of structure, or that depend based on that emulsion, different type of micelle formation should be there, different type of nanomaterials we can synthesize using that. So here this ternary phase diagram is showing here. So here's oil, waters and surfactants at different ratio, we can forms a different type of microemulsions that we can develop. So here's one it is showing. So if we use water 60%, oil 26% and surfactant 14%, so then this particular mixtures, a particular type of microemulsions may possibility is there. So we also can change other quantity or concentrations also, depending upon that a particular microemulsions would forms, and that can be used for nanomaterial synthesis. Okay. So here's when we are synthesizing the microemulsions by using oil, waters or any surfactants. So each component means that solutions that would form. So that solutions surface tension is very important. That liquid we are using for nanomaterial synthesis. So there sometimes we use electrolytes or organic surfactants. So each here you can see, if we use electrolytes, that actually increase the surface tensions of that solutions whatever that we have taken. So that surface tensions will increase. Okay. So surface tensions, if we use surfactants, so that surface tensions of that solutions gradually decrease up to CMC formations, critical micelle concentrations, and after that the surface tension of that solutions would remain the almost constant, you can say. So there is no changes of surface tensions by further increasing the concentration of the surfactants. And if we use organic molecules or organic solvents, so that also decrease the surface tensions, not significantly, but it also has a roles to change the or decrease the surface tensions of that solutes that we are using. Okay. So here's two different type of micelles I said. So one is this is my emulsions, one is micelle formations, water, oil water systems, water in oil systems, so inverse micelle. So and here different shapes of micelles. So the micelle I said spherical type of, this is by using surfactant. So here's spherical type of micelle formations is there, disc like micelle formations is there, or cylindrical types of also each possibility is there. Means that surfactant or amphiphilic molecules that will take for a particular means ratio of oil, water and surfactants for microemulsion formations, depending upon that a particular shape will forms or way of arrangements of surfactant is there, based on that the structure will forms. And lamellar type of, this is lamellar types. So this type of various shapes of micelles can be formed depending upon that materials, means surface surfactants, oils and waters that we have taken, based on that. So using these microemulsions we can prepare many materials, means cobalt, copper, calcium carbonate, barium sulfates. So or any metal oxides also that we can in a nano range we can synthesize by using this techniques. So here one or two examples are will show means. Okay, before that, these microemulsion techniques for nanomaterial synthesis, they that also can be classified or can be means when the nanomaterials formations is there, their mycelium formations is there with the help of surfactants. So the distributions of the surfactants means if we use the surfactants, that surfactants may form small myceli, that may be inverse myceli or small myceli formation is there. So that means if inside of that myceli any water is there, let us say, so then that water may contain some starting material, that is the inorganic materials or metals that we want to use to synthesize a particular nanomaterials. So here we will show there are, I said, many methods are there. One microemulsions method is there. So in that case, energy triggering, first one is energy triggering methods. In this case, the reactant precursor that would be encapsulated with a single microemulsions. This is microemulsions or mycelium formations is there. So here inside maybe water is present and this is surfactants. So inside, let us say, any metals, that may be alumina oxides if you want to prepare. So then alumina precursors we have to consider are that in that solution that particular metals is present in the form of small microemulsions. And then if you use some lasers or energy from externally, so then that metals in as a ionic form that would be present inside of that emulsion. So that would be converted, or that would be in presence of light, if that would convert into these metals to metals hydroxides. So that remains over there in the form of small materials, or in that range maybe 2 to 5 nanometers within that range. So that remains as a metal oxide or hydroxide would be there. After that, if we calcines or heat ups, then any heat up or calcines, so then surfactants or other compounds would be disappears, and then small nanomaterials or nanoparticles we can synthesize by this way. Here external triggering agents, that was laser, that was used to for that particular reactions or conversions. Okay. So here nanosized gold nanoparticles we can synthesized by using laser photolysis, that way we can synthesize. So here gold precursors you have to take, and then this type of microemulsions will be formed, and then by using some laser photo lasers we can convert that gold ions into gold particles in the form of nanomaterials. And second one is the one microemulsions, this type of microemulsion forms plus reactant methods, means instead of lasers or source for that particular reactions, externally another reactants, if the reactions means A plus B would gives AB, that is our product. So one that reactants would be in the form of this type of myceli, and another second reactant that remain in that solutions. So then both will come in contact and that reactions will form. And see here's the second reactant that we control to, if we stop then there is no reactions, means controlling way we can control the size shape of that particular metal, and that would be converted into desired nanoparticles. Okay. So here sodium hydroxides we can as a precipitating reagents for any metals, let us say alumina, aluminum hydroxides would be theirs. So that, or any nickels, nickel hydroxides, or any cobalts or any oxides if you want to prepare, then from that starting metals, if by using hydroxides, one mycelium formations is there, another is in solution, sodium hydroxides in solutions, and if cobalt metals, that is ions that remain in myceli, both will react, and thence we can form nanomaterials by this way. Okay. So and third one is the two microemulsions. So in separately, let's I said A and B, that is going to formations of this is our products, the nanomaterials. So here's A would form say one microemulsions, B also we can, means two different containers we have to consider, two different microemulsions will form, and after that we will be mix them together, and then once it is mixed up, then reactions would be very slow, and then this the whatever the our finals nanomaterials that can be synthesized by using two separate microemulsions methods by this way. Here microemulsion 1, microemulsion 2 that we form separately, and then mixing two microemulsions we can and conduct the reactions, and here's the reactions means one reactant to another reactants. When they come in contact, then reactions will take place, and that one reactants to another reactants that would be transferred through fissions means reactions will be take place, and then one reactants will interact with the other reactants, and by that way means by precipitations or the particular reactions that nanomaterials will be formed. Okay. So here's that mechanism means how one microemulsions another microemulsions by interchanging their reactants among these two droplets. This is one reactant, this another reactants, and after that they will react nucleate formations and then Brondate particles. After that, if we calcine or heating at a particular temperatures, then small nanoparticles we can forms using this microemulsion techniques. So okay, so today is up to this. Thank you.